IUPAC nomenclature rules to it. I believe that you should come to a name for it based on your rules. Not cyclohexane. It's close. It's cyclo and it's 6 carbons, so I like cyclohexa. But it's not an ane because it has double bonds. And so we would call this molecule 1,3,5 cyclohexatriene. So the hexa again means that Brecken counted 6 carbons, and the cyclo means that they're in a circle or cycle, I don't know. So they make a hexagon shape. And then you can see that if I call this carbon number 1, I can go around. Doesn't matter if I go clockwise or counter or anti-clockwise. There's a double bond at 1, there's a double bond at 3, there's a double bond at 5. So there's enes at 1, 3, and 5. Because there are 3 of them, I use that Greek prefix tri. So 1,3,5 cyclohexatriene. Karthika, that's more joy than I'm used to. So yesterday you actually learned, yesterday by which I mean I did this yesterday, you did it 2 days ago. You learned a reaction that we associate with identifying alkenes. Do you remember what that was? So we had 2. Yeah. Y'all are thinking about adding bromine water and it would decolorize. And y'all are saying this is an addition reaction. And so if this was an alkene, the expectation would be that we would decolorize bromine water. Is that fair? One of the first reasons that I know that that should not be called 1,3,5 cyclohexatriene is because it does not undergo addition reactions. Is that a chemical or physical property? It'd be embarrassing if you all screamed it out at the same time. It is on the freshman test tomorrow. Chemical or physical property? Chemical. It doesn't do this reaction. So one of the reasons that I'm not going to call this a triene, one of the reasons we call this molecule benzene, is because it doesn't do addition reactions. So if my characteristic test of alkenes is they do addition reactions, and I can see that by decolorizing that orange water, this does not do that. Consequently, not feeling like it's an alkene. Now, a second thing you might do is tell me to give you guys data booklets, because I know you enjoy it whenever you get to do data booklets. I feel like a small class, I feel like it's a good idea. You're going to go to table 10. That molecule is called benzene. The rules that we have learned before, we would call it this goofy 1,3,5 cyclohexatriene, but we don't call it that. We will call it benzene by the end of today's class.
Like the entire thing.
The whole thing, that 6 carbons and 6 hydrogens is called benzene. Yes, this is SL. 10-point dose. Karthika is laughing because she remembers that time that she looked at table 10 and thought it was table 11 and got all the enthalpies wrong. Oh, the embarrassment.
But I fixed it.
I didn't even know you did it. I'm just making things up.
You did assume I made any mistake in calling her.
So tables 10 and 11 look identical to each other. That's a sadness in this book. We're looking at table 10 right now. And what I notice is that it has some bond lengths The bond lengths are all reported in picometers, because why the heck not? And it seems to me that if I found a carbon-carbon single bond, I could look at this table and tell you how big it should be. How big should it be? 154 picometers. And if we look toward the bottom of the table, we should be able to find the length of a carbon-carbon double bond. 134. What we find using microwave spectroscopy is that each and every one of the carbon-carbon bonds, if Emma does not say carbon-carbon bonds, Emma does not get this mark. All carbon-carbon bonds are equal in length. Can anyone find the answer in the data booklet, or do you just want me to put another sig fig in there to dazzle you? 140?
1
No.
Oh. 154.
It's still not 154.
That's the length of the bond.
So we expect,
Oh, it's this
so all the carbon-carbon bonds are equal in length in benzene. We expect them to alternate 154, 134, 154, 134. We don't find that. We find they're all the same. I claim the answers in the booklet, but now we're going to write down the answer I memorized. They're all 139.7 picometers. Everybody knows that answer. All of the bonds are the same length. Have you ever seen that before? Bonds that Lewis draws as different, but we know are the same length. It's resonance. We saw it in ozone. Because it's a 1.5 bond, exactly. So if you looked at the molecule ozone, you would experience the same thing. The data booklet would guide you to believe that those two bonds were different in length, but experiments suggest they're the same in length. That's because we can draw two resonance structures, one with a single bond on the left and a double bond on the right, one that is the opposite of that. And so we think that there's really some sort of an average. You might draw like that. Yes? That is a better picture. So this is an example where Lewis leads us astray because Lewis doesn't accommodate resonance structures. So I believe that I should be able to draw a resonance structure of this molecule.
So even the double bonds are 1.5.
All of the carbon-carbon distances. I know you guys see that single bond, and that's why the conversation went kind of so poorly. Like I could feel it in real time how it was not going good. So I'm not trying to, like it's a hyphen between the two carbons, all the carbon-carbon bonds, not the carbon-carbon single bonds. So if I wrote it out, would that be better? But no one would ever do that. That's what I'm trying to say, without giving you the indication that it had to be a single bond. Again, that's because of resonance. We could draw the double bonds in this position or in this position. Both would be appropriate Lewis structures. In actuality, we think it's the average of those two. The average of a double bond and a single bond is a 1.5 bond. And so some of you were talking about taking an average, which would have gotten you to 144. If you look at the bottom of the sheet, though, it tells you that this is 140 picometers in benzene. So this is one of those cases where you would know the right answer, but if the question were ozone, you would just take that straight average. So taking the average is absolutely the right spirit, but because the answer is in the data booklet, in this singular example, I would just use the answer. I'm not going to try to outthink them. The subject of my thesis was alternating double and single bonded compounds, so this is like a thing for me. Okay, so what I've described is that if I drew a structure, I would expect that the bonds would be alternating in length, long and short. And what I found is that benzene is hexagonal, it's planar, and all of the carbon-carbon bond distances are 140 picometers. They're equal. Would that be an example of a physical or chemical property that would make me believe that there weren't double and single bonds, but instead something else going on here? Absolutely, this is a physical property. We're not changing the molecule the way we'd be reacting it with something. Here we're just saying this is what it looks like. You can typically get this mark by saying any one of those three things, but I tend to say all three. I'm a big chicken. A giant. Physical fact. You ready for another physical one? If our structure was 1,3,5-cyclohexatriene, I believe that we could make 1,2-dichloro 1,3,5-cyclohexatriene, and I believe that we could make 2,3-dichloro 1,3,5-cyclohexatriene. Those names are abhorrent. Use that word twice now, like the quotient rule. But to give you an idea of what this might be, this is saying that there's a double bond at position 1, so we can call this 1 and this 2. The first molecule I've written has a chlorine here and a chlorine here. That would be 1,2-dichloro 1,3,5-cyclohexatriene. And the other molecule that I'm trying to convince you might be worth discussing is instead a 2,3. Is that clear enough what the distinction is between them? I'm just talking about putting the chlorine in two different spots with regard to those bonds. And I'm curious, are those structural isomers? Yes, are these two molecules structural isomers? Same molecular formula. I've drawn them as different in this Lewis structure, but the back table is saying that maybe I'm lying. If I believe that all of these bond distances are equal to each other, then instead of implying that these two chlorines are a little bit closer and these two chlorines are a little bit farther apart, making the two molecules different, if this is really a true hexagonal structure and each of these bonds is exactly the same length, then these two molecules are exactly the same molecule. And so in fact, these two things are not structural isomers. They are identical. This is a physical property that indicates that benzene is a special molecule, that it is not 1,3,5-cyclohexatriene. And we simply say there are not two structural isomers of like a 1,2-dichlorohexatriene. We have three reasons right now that I think this molecule is special. Reason number 1 was it doesn't seem to be an alkene because it doesn't do the reaction that I think alkenes should do. It doesn't undergo addition reactions. That one's very important to me. Reason number 2 is that the structure isn't consistent with having 134 picometer short bonds and 154 picometer long bonds, but instead it's consistent with having a perfect hexagon. That's a physical property that indicates to me that this isn't behaving like alkenes. Another physical property that's indicating to me that this is a little bit special is kind of hard to write down. Like I understand it pretty well in my head, but if there truly were real double bonds and real single bonds, if I put the two chlorines on a double bond, I would have a different molecule than if I put the two chlorines on a single bond, because the chlorine distances would be different. But what we find in benzene is that the distances are the same and the molecule is the same. These both describe the same molecule, one correctly, kind of, but not really, and one definitely incorrectly. Does that one make sense to you?
Yeah.
Okay. So I find this one awkward to write. It's not my favorite, but if we're ranking them, I started with my favorite. My favorite is does not do addition. My second favorite is a hexagon. This is my third favorite. I can draw two pictures and I think I can convey this idea between pictures and words. Remember, there are no rules about writing well on an IB exam, and pictures work. So don't stress about like draw some circles, draw some double bonds, say this one would be smaller than that one. It's gonna take more words than I want to spend. I only have about 90 seconds to convey that idea. And I'm a little nervous, but hexagon certainly didn't take 90 seconds. Just wrote that right now, hexagon. Felt good about it. Planar hexagon? Yes. So there's a fourth reason. It's also a chemical property. And this is the doozy. And this is why you have a data booklet, except now you are going to flip to table 11. And what I would like you to do is I would like you to calculate the enthalpy of the hydrogenation of cyclohexene. Using the bond association enthalpies in table 11. Is that a clear-ish question? Okay.
Hydrogenation as in you're adding.
I love that question. Hydrogenation is an addition reaction. We are adding hydrogen. So what Aditya is saying is that she's taking cyclohexene. So that means we have a cycle of 6 carbons. And somewhere along it, it has a double bond. So I'm going to draw in all the hydrogens because I'm trying to be a good person. Is this molecule planar or not planar? It is 100% not planar and not hexagonal. You're making me cyclohexene. I don't know if I counted right. There should be 2 carbons that are different than the other 4. Those are the 2 that make the double bonds. So you can see that this guy is sp3 hybridized, and this guy is sp2 hybridized. That's a p orbital ready to do something magic. Bonne chance. When you go on to take some organic chemistry at university, you'll learn to draw the chair and boat conformations of cyclohexane. Shortly, Karthika will be able to model those 2 for us. Chair and boat. Unfortunately, we don't enjoy that in this class too much. I just want you really to appreciate that benzene is flat, and these other things are very much not flat. These other things are sp3 hybridized. They are trying to make little tetrahedra. They ain't not flat. Benzene, on the other hand, each one of these carbons is sp2 hybridized. When something is sp2 hybridized, that means it has an unhybridized p orbital, and all of these p orbitals are lining up to point directly out of the plane of the board to allow those pi bonds to form by side-to-side overlap. So all of the p orbitals are parallel in benzene. That is what's driving it to be planar. sp2 things are always planar. All of the carbons in benzene are planar. But you, poor souls, are trying to figure out the enthalpy of that reaction using table 11 in your data booklet. So Aditi told us that hydrogenation was adding H2 across a double bond to saturate a molecule. This saturated molecule is called cyclohexane. It is an addition reaction, and cyclohexene on the left is in fact an alkene. There is no resonance there. There is only one way to draw that Lewis structure. That picture is kind of poor. I apologize. When you take organic, can you all picture Sophia with her little template that's going to draw perfect hexagons and perfect little cyclohexane chairs? They just make like little plastic things, like protractors, except for organic chemists. They make paper for organic chemists that instead of having like lines or grids, has hexagons. It's a thing. Do you have an answer yet, Bobo?
No, I just looked at the organic.
Yeah. So the idea is that if we had a short bond and a long bond, so if benzene really has this structure, if you put a chlorine here and a chlorine here, they'd be next to each other, right? They'd be quite close because this is a short bond. All that stuff. So you could make another molecule that looks like that, and put the chlorine here and here. So these chlorines would be far apart, and these chlorines would be close together. The way that we would name these, I wrote on the board to the best of my ability, but what we find is that these two molecules are actually identical.
Oh, okay.
Carbon bonds the same. So you just need to say something along the lines of there's only one, and one type or not two. I find the sentence hard to read, so I need to draw pictures. Yes. Yeah. That's a good one. This one sucks. This one is by far the hardest, right? It makes sense, but there's just a lot of information. But that would be easy. That's why you missed it. It's not too long at all, right? I mean, it's really pleasing me that it's taking a long time because I don't really have a whole lot to say, but what the heck is going on?
It's bond, it's bond breaking minus bond making.
Breaking minus making. A? I mean, you're inspiring me to get a calculator, but no. Did you break the H2 bonds? Did you break the carbon-carbon double bonds? Did you make your carbon-carbon single bonds? You made 2 CH bonds?
Wait, where?
You have to make 2 new CH bonds.
Dr. Nancy,
That's me.
why did you circle those carbons on that board?
The carbons are circled because that was supposed to represent the head of the p orbital coming out toward you.
Okay.
All of the p orbitals are parallel to each other in order to make that double bond. The p orbitals have to do the side-to-side overlap. But in benzene, because of the resonance, you have to be able to overlap to your clockwise and your counter or anti-clockwise side. All of the p orbitals are parallel. You make a molecular orbital. There's delocalized electrons. There is resonance. Anytime there is resonance, there's delocalized electrons. Those are synonymous.
Is the bond breaking 692?
I don't know.
Why did you make this shape?
That is the actual 3D shape of this. The team in the middle table is trying to make me some cyclohexane. Y'all are trying to make me some cyclohexene.
So are we making that one? The one on the left?
You guys are making the one on the left. The middle table is making the one on the right. And we're just being, it's fine. She might need some more hydrogen. She's doing herself.
So then are the white things the hydrogens?
The white things are the hydrogens.
Are you doing this? And I don't know what.
Oh, that seems like a much better answer.
But okay, so I did the double.
Yeah, double bonds, hydrogen.
Hydrogen minus.
Yeah, all of those. Yeah, I like parentheses on there, but you did it right. I mean, you did it, you just,
But it should be a positive.
I think it should be negative. I think it should be next to them. We're breaking a weak bond and making a strong bond. I agree with your answer. I would have said 120 if like Audrey put a gun to my head and said, what is the answer? I would have said 120. I am happy with 124.
Is I be okay with it?
Okay, what?
Is I be okay with it?
That would be, so, give me 1 second.
Yeah.
Too big, too much. So, if the question in IB is, hey Emma, do this problem using table 11, then they expect your right answer.
Okay.
But this question is, how do we know that this molecule isn't an alkene? Like, I'm still trying to prove that that's in, so that's why I have some round numbers in my head, but I don't know the exact number. I promise it'll be a pretty good story. I think you did the calculation
Will
right.
we get asked like those questions just so we know?
Provide
like, steps?
evidence.
Oh, provide evidence and then you're or evidence meaning like backup for how you know that it's not.
I'm saying, so the question I'm trying to help you with is provide chemical and physical evidence that this molecule is benzene, not cyclohexatriene. And yes, we are working on number 4. And so we are reviewing something from your dark past.
Okay.
Okay, so Emma and I are good. Karthika's playing games on her phone with Rita, who's undoubtedly also in class. So I heard that I had 3 bonds that I had to break on the left, or that is one way of approaching it. Here there is a double bond between carbon and carbon, so that would count as 2, and a single bond between hydrogen and hydrogen, that is the 3rd. On the right side, I'm making, a single bond between carbon and carbon, and 2 single bonds between carbon and hydrogen. So typically, I find that the number of lines I break is equal to the number of lines that I form. If I don't find that, I get very nervous. Now, watching Aditi work really hard, like she counted the total number of bonds on the left and the total number of bonds on the right, but she is just much more willing to work hard on something than I am. So you have a choice here. You can say that you're going to break 10 CH bonds. You can say that you're going to break 1, 2, 3, 4, 5 CC bonds. You're going to break 1 C double bond C and 1 HH.
Is that 5?
That's a 5. And you can say over here that you are going to make 12 CHs, 6 C single bond Cs. I think you're done. Did you not just say my name? Okay, I'm staring at you like you said my name. It's going to be awkward if you didn't. No, or you can say that, some things aren't different between them. So you can sort of subtract what appears on both sides. And so the 10 goes away, it makes that a 2. And the 5 goes away, and makes that a 1. And we're back to the 3 lines that are different between the 2 pictures. On the left side, we have a double bond and an HH, 3 lines. And on the right side, we have 2 CHs and a CC, 3 lines. And so looking at table number 11, we're going to take bonds broken minus bonds formed. The carbon-carbon double bond is 614. The HH single bond is 436. So we would get 1 mark for writing down 1050 on our paper. On this side, the carbon hydrogen is 414, and there are 2 of them. The carbon-carbon single bond is 346. We would get a 2nd mark for writing down 1174 on our paper. And then we would subtract and get our last mark of negative 124 kilojoules per mole for what is traditionally a 3-mark question. Use table 11 to, solve this ugly problem. Are we happy or sad about this? Audrey's sad about this. I don't know why. I don't know. I felt like I just showed my work. Where's my cyclohexene?
We're still. Right, because we're writing those too. Hold on. What does that say? 346?
They have flat, so it's not flat.
It's 117.
So I'm trying to give it a little character.
174.
I'm not super good at this. I seem to be making vote like a superstar, but I'm not making share very well. They're meant to be on both sides. So this has to be really similar to the structure of your glucose, right? Glucose bonding to be an oxygen. Right there, right? Okay, so if you have successfully gotten my negative 124 answer, the next question that you're going to answer for me is not the hydrogenation of cyclohexene, but the hydrogenation of cyclohexadiene. So I'm going to put 2 double bonds in there. There's going to be a double bond, a single bond, a double bond. That's still just an alkene. It would still undergo addition reactions, but we're going to try to calculate the enthalpy of hydrogenation of cyclohexadiene. Wow, this class is fun. This is why I go to math classes every month. It's so much more enjoyable. Isn't it?
We get like
Oh. So we call these guys up and downs. We call them the axials. We call these guys the equatorials. They only complicate it in different ways. And when you draw the glucose, you just draw that straight up and down line. Try to So the back table successfully made cyclohexane. If you want to see it, my only statement was it ain't flat. I hope you will agree with the statement, it ain't flat, planar. The carbons aren't flat and the hydrogens are certainly not flat. This molecule is beautifully 3-dimensional and perfectly made. Oh, she's taking videos of me. Oh my God, I'm gonna be so flippin' famous someday.
Yeah. It's been shared with you.
So video?
Yeah. Videos on it.
So do you get them unlisted? So you have to give the link to every single one.
Really?
Yes. That's what we were trying to tell you last year. What?
Look at your face.
What?
Dude, those are such my feelings. Like I try to make things so easy, and then you guys are like, "Oh yeah, that's not easy at all." It's like,
but I tried so
That's
hard.
like a violation of like, I don't know, video consent.
Texas is a single party state, so Moab can creepily tape record each and every one of your phone calls
What?
without your consent.
Dr. Hennessy, do you consent to me making them public?
Yeah, she needs to.
I think we need one more of them. And then, oh wait, no, hold on. No, this is, I don't know. We try to make a double bond, but like.
Yeah, I thought it was very clever, the double bond action. Yes, she is an amazing person. Do you see how this side is starting to get flat? My model kit isn't great, but like this is starting to look trigonal planar, and the rest of this is not. it's still looking quite tetrahedral. As we put more of these together, it's going to get more and more planar.
Okay, what? Put more of the double bonds together, it gets
Yes.
more planar.
Yes.
Okay, let's just observe.
We'll make some benzene for you.
Okay.
What'd you get? What'd you get? Nope. Did you do 2 H2s?
Yeah.
So that's what we have in mind. My pictures are getting lazier and lazier because that's where I am right this minute.
Wait, so we're calculating the enthalpy of the hydrogenation of what?
Cyclohexadiene.
Cyclohexadiene.
Cyclohexadiene. I drew in the hydrogens so you know you could count them all. She's getting a be in charge, Randy. Okay. I'll be back in a second.
Do I scream it out now?
No.
I just stretched.
Hey, Ramy, how'd they do? It's been my experience this morning also.
I added
Oh, good.
too many carbon hydrogens. So that's it.
Hey, my girl Emma and I agree.
Wait, don't see it.
Front of the room, kicking butt, taking names. So let's play the same game. What are we breaking? We have 1, 2, 3, 4 CC bonds. We have 1, 2 C double bond C bonds. We have 1, 2, 3, 4, 5, 6, 7, 8 CH bonds. And we have 2 HH bonds. And on the other side, we have 1, 2, 3, 4, 5, 6 CC bonds and 12 CH bonds. Now Ramy thinks that I should, go a little low energy and cancel out things that appear on both sides. So she suggested that we get rid of these 4 CCs and call this 2. And she suggested that we get rid of these 8 CHs and call this 4. So we would go into our data booklet and we would look up C double bond C and we would get 2 times 614, that's 1228. We would get 2 times 436, that's 872. We would add those together and we would get 2100, mark number 1. For mark number 2, we go into our data booklet, we look up the CC bond, it's 346. So we would get 692. That was hard. would look up CH, that's 414. So we would get 1656. We would add those two together. We get 1323.48. Second mark, we would subtract bonds broken minus bonds formed, and we would get negative 248 kilojoules per mole. Yeah.
Why are we not doing, 4 times 2H, like the H is wrong? Because.
This
Yeah,
molecule
it's 2, it's not 2.
just looks like this, right?
Yeah. For some reason it was 4.
It's okay.
Okay.
We're getting to this, or is this just too painful? Where are we? Math test just too hard?
Isn't it?
What?
Okay.
You haven't done it.
I did it today.
You did it today.
First period.
Yeah, Mohawk's in the math class I like to go to.
Oh, right, you're in the other math class.
You're in the math class I like to go to. I don't know what the other one of those is.
Simple.
Period.
It's 8? Yeah, I can't go to 8.
No, I'm in 1.
You're in the math class I like to go
She's
to.
in
I can't go to 8, I teach the freshmen.
That was scary. They were walking around doing like random things. I was like,
Wait, so who was teaching your class that you were like walking around?
I must not have been teaching.
he doesn't teach
Like in
this
math?
period.
No, like on this day, your last period. you
Oh,
were,
I'm
like,
off 7.
Oh.
Off 7.
Could you ever just go home?
Apparently you losers are allowed to go home now, and we still are not. That is,
We're
that
allowed
is
to go home if we have study hall last period.
if your parents contact Jennifer Thomas,
Oh, yeah. Then you're done. Yeah, that's always been a thing.
no,
Oh.
that has vehemently been disallowed.
Yeah, seniors just did
Vehemently,
it
you are
last
on
year.
campus from 8 to 3:30.
Oh.
And now it's like, if your parents are chill with Jen Thomas, then feel free to come late or leave early.
No way. That
Way.
is so.
Wait, actually, I have TOK
You
last.
Yeah,
must
TOK
get
last,
permission from
it's turning
Jennifer
into a
Thomas. I
study hall.
cannot give you that permission,
Go
I
for it.
have no power.
I have TOK
No,
last.
like you just, the parents have to initiate the conversation, so it's not gonna go out in like an all-student email, hey, if you have first period study hall, feel free to come in at 9:45. But if your parents are like, Karthika would really benefit from staying home on, the days that she has study hall, would it be okay if she were to, slide in around about 9:30? My understanding is that Jennifer Thomas will say yes.
But you can't do that if you have like second period study hall.
No, I do not believe you can leave in the middle of the day.
I have I'll have TOK last period.
I could leave for second period. I will now.
What do you think you won't do that?
Please do do that.
But like, didn't you guys live COVID life? Is it that good to be at home all by yourself,
Oh,
working
yes.
all the time?
Like we're go out.
You know,
Go
one
out.
thing I lost was my
Home is outside of school.
So masters of pattern finding, if we had the molecule 135 cyclohexatriene, what would the enthalpy of hydrogenation be? I can't hear you, Amy, but I feel like you could be saying fantastic things.
Would it be 4? No. It
It would be like.
Dr. Macy, what are you
The
laughing
math skills are a little
It would be
questionable.
like
Wait, what is the question again?
negative 3.
The question is, if we were to hydrogenate cyclohexatriene, how much energy would be released, Emma Wilson?
Like
So this is like a table.
negative 360 or 372.
It's a very.
Because look, you add 124.
You add 124 each time. I felt it. I got your pattern. It was a fair pattern. thought this could take like most of class. Everyone thought we would be done with this, and now be on to the next thing.
So how does this add to number 4? It's a chemical.
We're not there yet.
Wait, and those numbers you put there are in kilojoules per mole?
All of those numbers are in kilojoules per mole, friend. You guys solved for 2 of them, and then we were able to predict what the next one might be because we are rock stars, right? Did you feel like a rock star when you did that? I didn't feel it either. But when we tell the story of our day, we'll talk about how astute we were. In actuality, if one were to hydrogenate the molecule we know and love as benzene, we receive 210 kilojoules per mole for Sophia.
What? Wait, what is that one? Benzene. That's benzene.
Okay, so instead of calling this cyclohexatriene, if I draw the picture we associate with benzene, it's supposed to look like resonance. It's supposed to look like I don't know where those double bonds are. All of the bonds are equal. It's a perfect planar hexagon. It doesn't undergo addition reactions. When you hydrogenate it, you also get out a whole lot less energy. What did the act of delocalizing the electrons do? So instead of the electrons being trapped on me in a double bond or on Brecken in a double bond, the electrons are allowed to scooge between us, move, explore the whole hexagon. What did that do to the energy? It lowered it. We refer to this as a pen that doesn't work, and we refer to this energy difference as the resonance stabilization. So to get back to Emma's, what the heck do I write down as the 4th reason? What you need to be able to convey is that the enthalpy of hydrogenation of benzene is much lower than we would expect for the cyclohexatriene due to the significant resonance stability.
So cyclohexatriene is like what the name is if you assume there's no electron resonance, and then benzene is like the one.
That's right. So there is no such molecule as cyclohexatriene.
Okay.
That's what we would call it in the absence of this resonance stabilization. And we now have 4 pieces of evidence that lead us to call this by its own unique name, benzene, because this does not convey the truth.
I need to change my highlights. I think I've marked the minutes.
What she said on the board. I don't know what she said. Okay. So, cyclohexatriene is what we would call this molecule. If the electrons weren't delocalized. If there wasn't resonance. If the bonds were unequal.
This molecule is a benzene.
All of this is false. We call it benzene. I did my best, Amarachi, I don't know. And yes. Benzene is an example of an aromatic compound. Aromatic means that you have electron delocalization, and it kind of means you have a benzene ring. The opposite of aromatic is aliphatic. I do not expect that word ever to appear on anything. All of the molecules that you have dealt with so far this year have been aliphatic. This is the only molecule we will deal with that is aromatic.
What's aromatic?
I mean, it has to do with how it smells, right? But it means that you have resonance and alternating double and single bonds.
So like
Anything with carbon, it has to be carbon. So it is carbon-based, alternating double and single bonds. So we shall call this molecule benzene. Benzene does not undergo addition reactions. Benzene is fantastically special.
And it's aromatic.
It is aromatic.
What was the opposite of aromatic again?
Aliphatic.
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 And what's the
That's a word I think you never need to know, but you know, you see it every now and then and you're like, what the? Like all of you people who want a doctor, like your whole life is vocabulary from what I can tell. There's a ton, right? Glands are different by virtue of how much the cell like decomposes when it squirts out goop. That's disgusting. And who knew you needed 3 words to describe that? I don't know. How hard anatomy is.
Right. Is it RRH?
Oh my god.
When you like vomit out or splurge.
Hemorrhage.
Oh yeah, but that's why like next class person I have like a dog.
This is like it's one of them.
Yeah, you have 6 balls. So if you drop this here, you can't use that. If you're trying to prove that this is like compare with using this mode, that would make sense. That's me.
Yeah, it's like
Why does the people has electron lower?
So whenever you pin electrons into a small region of space, their energy is quite high, they're very unhappy. And whenever you allow electrons to sample a big region of space, they're much more relaxed.
it's called
Could you? Okay, so like it's like less than that. So like there's like a lower electron.
Well, yes, it's more spread out. It's spread out over a larger area.
Okay, so it's like less stress.
Easier to break. I mean, sure, it is more stable as it is. Yeah. So benzene is actually extremely hard to break. So
why is it hard to break?
I'm about to tell you. So the question might have come to your head, when I draw benzene, I can consider it like an alkene, so why can't I hydrogenate it the same way? Like, why can't I take benzene and turn it into cyclohexadiene?
What does cyclohexadiene look like?
It's the it's
The giant.
Is it the middle one?
okay, I'm gonna do it with bromine, so I'm doing something useful.
Wait, so we're doing, yeah. So we're moving on from benzene.
So now I'm taking benzene. I'm drawing it in the newfangled benzene way to show that resonance, to show I'm not calling this a triene. And I'm gonna try to add bromine to it. What does it not do? It doesn't decolorize benzene because it does not undergo an addition reaction, because it will not form this molecule. Bueno? Does everyone agree with that statement?
So it can't undergo.
It cannot undergo addition reactions because we don't believe it honestly has double bonds. So if Mohab put benzene in there, thinking in his head that benzene could be thought of like this, and expect that addition reaction to happen, Mohab would be disappointed. Instead, what Mohab finds is that if he makes it react with bromine, he must do so in the presence of course, ferric bromide. That's obvious. And then he will not get that product on top. He will get that product and HBr.
So, wait. Why are we adding iron?
It's the catalyst that allows this reaction to happen.
Oh.
The catalyst is required for benzene to react with bromine.
So
It does not
addition-
undergo addition.
Oh, but that's not called addition?
This is not addition because we did not add across a double bond and saturate the molecule. We started with benzene. What did we end with, everyone? Benzene. Everyone who still sees that we have benzene. We didn't break the delocalization. We didn't lose a double bond. This is a process wherein a hydrogen became a bromine. So how might we refer to that? It is substitution. We call this electrophilic substitution. You can also call it electrophilic aromatic substitution.
Wait, so this is called
Electrophilic aromatic.
electro.
Feel like substitution. You can also put aromatic in the
I just feel like some people call it EAS, electrophilic aromatic substitution.
Other mechanism.
This is the final mechanism you'll need to learn.
Yes.
Okay. Hold on.
What is the other substitute? Oh, nucleo.
That's right, we have nucleophilic substitution and electrophilic substitution. We have electrophilic addition. There is nucleophilic addition and elimination, but it's not in the syllabus, isn't that a bummer? So we don't learn it anymore. That is how you make an ester, so you did do it, but we don't have a mechanism for it, and I'm totally cool with that. We don't need another mechanism. But that word electrophilic is required, so if you just call this substitution, sadness will ensue. Yes?
On the left, on the teal color,
Yeah?
when you add that H and the blue on the top of the benzene, is that two H's or did you just drop?
That's a plus sign between it and the bromine.
Okay. I have very.
It was just in a bad spot. Yes?
And then this is the bromine water,
That is not, so the top one is, can I react benzene with bromine water? The answer is no, bromine does not undergo addition reactions. The second one is, Brecken is a stubborn son of a gun and he wants to react benzene with bromine, so we found that there was a catalyst that would allow him to do it. The catalyst is ferric bromide, and when he makes the benzene react with the bromine, it still doesn't do addition, because it is still not an alkene. It has its own special reaction. The only thing that does this reaction is benzene. This is the reaction you have to know for benzene. There are in fact two reactions you have to know for benzene. One, you have to be able to write that down. I have never seen a question about it. I'm sure that I can find Jeffrey Noose asked one. But as far as I know, the mechanism for that particular reaction is not in your syllabus. So the bromination of benzene, the mechanism, what the ferric bromide does, is not in your syllabus. I'm happy to show you if you're in the mood, but I'm going to show you the one you have to know first. And then we can like abstract to the one we don't have to know if you need a second example. So I don't care for the benzene part of your syllabus, because ultimately what I'm telling you is there is one question they can ask and you have to memorize the answer. When I mark paper 2, this question is left blank more than any other question, because there's like one example of it and you either suck it up and memorize it or you don't. There is no making this up. There is no like things are going to rain down from you from the sky and it's going to come to you. There is just the pain of you need to know this if you want to get these marks. And so this is called the nitration of benzene. This is an example of electrophilic substitution, but what makes this example important-er is that it's the one you actually have to write on your test. So this is an example of electrophilic substitution. Why they didn't choose the one with bromine is anyone's guess. They chose the one with nitrogen. I don't know why.
Wait, so the one that we just learned is not the one that we need to know?
You need to know that that reaction will occur. You need to know the reactants and the products.
Okay.
You need to know that the product of electrophilic substitution is different than the product of electrophilic addition. But you do not need to know this mechanism. The mechanism you know for benzene is a second example of electrophilic substitution, and that example is the one you need to be able to draw. So we're gonna practice drawing the one that we have to draw, and then y'all can take a vote on if you wanna practice other things you don't have to draw, just for joy. Audrey's gonna be like, yeah, let's go. We're gonna take benzene. And we are going to react it with nitric acid in the presence of concentrated sulfuric acid at a temperature of about 150 degrees. Someone may want to look that up. Pulled that from the clouds. I know the answer to the question. If you do it too hot, what happens is that you get multiple nitro groups on there. We'll double check that. I know we need a temperature. Audrey might have the answer in a second. And you are going to make nitrobenzene and water. Everyone can double check that my equation is balanced. I like to draw what I call the special hydrogen. How many hydrogens are on benzene? There are 6. I draw the one that's going to do some magic. I draw the one that is being substituted. I hope you can all see that this H is being substituted by that nitro group. If we count, the left side has C6H6 and HNO3, and the right side has C6H5NO2 and H2O. And hopefully you'll see that both sides have 6 carbons, 7 hydrogens, 1 nitrogen, and 3 oxygens. Balanced chemical equation, 1 mark. The mechanism for this is going to happen in 2 stages. In the first stage, we need to create an electrophile. An electrophile is something that likes electrons. Benzene is going to find that electrophile in space and do something to it. So step 1 is make the electrophile.
So,
It shouldn't exceed 50.
so step 1.
That wasn't a terrible mistake. Easy fix, single finger.
So this is the step 1 of nitrogen and benzene.
Yes, so we are going to do part 1. So part 1 is going to be subtitled Making the Electrophile. Molecule hopefully looks like HNO3. Does that look compelling to you? No. Nitrogen can't exceed the octet. So nitrogen here, if you want some partial charges, this is a plus and this is a minus. So we're all neutral. If you want formal charges, I'm cool with it. If you don't, I'm cool with it. Nitrogen can have 4, but its formal charge will be positive. We can calculate formal charge on everything if you want, but Karthik is going to actually start throwing fists soon. I'm a little scared, I won't lie. I don't even know what to draw now, she is so scared. Hey, this is a crazy reaction. I'm taking an acid and I'm mixing it with another acid. One of those acids is stronger than the other acid, and what will happen is still a Bronsted-Lowry reaction. We are still going to have one acid donate a proton to the other acid, and in this case, sulfuric acid is the winner. It is the stronger acid. So sulfuric acid will appear as its conjugate base. It's the acid in this statement. And oh my God, nitric acid is actually behaving as the base.
So,
Wow.
So this, HNO3.
Sorry. this reaction.
But is
Sulfuric
it-
acid is so acidic that by comparison, it is going to be the thing that has to take the proton.
What is like the real conjugate bases are only gonna be on one?
This is a conjugate base, and we are now gonna draw the conjugate acid of nitric acid, because I hate you guys.
Okay, so Bronson, Lowry.
Yeah, we know.
I think it's better not to have all of those formal charges in there, but only to show you the newest of formal charges, the positive on the oxygen. So if I were in charge of this world, I would only be showing you the positive on the oxygen. That is a disgusting intermediate. It is very unhappy with its lot in life. Does have a lone pair on it, I shall show now. And what happens? Oh, I probably should have done other electron push. Well, what happens is that this goes here.
So, okay.
So this is step 2.
This is the second step of the first part of the nitration of benzene.
Wait.
Yes,
So-
sweet, sweet.
The one on the very right is the conjugate acid. Or is it the conjugate acid on the very right?
This is a conjugate acid. I threw in some arrow pushing in the first so that you wouldn't think I was lazy. We don't really need it.
Is that all together or is there an addition?
There's an addition sign. Making my arrow pushing better and better. That looks really superior to me. Here, I won't even draw this.
We don't need that?
No, you don't. I thought we were gonna need it, but we don't need it.
Will we need it later?
No, we'll never need it. I had a lone pair here on the oxygen. It's not incorrect. There is a lone pair here on the oxygen, but it didn't do anything. So the magic of me having a, free eraser in my finger was just getting rid of something that was extraneous. Just trying to keep it tight. So this was step 1, making the electrophile. What do you think the electrophile is? This is your sweet, sweet electrophile. I believe in the last 12 years of papers, I can find one example where they expected you to draw arrow pushing for this. I can find a couple examples where they expected you to be able to draw the Lewis structure of your electrophile. And I can find mostly examples where you need to be able to write down that HNO3 reacts with H2SO4 to form the nitronium cation. Or no doubt you guys say cation. Water and hydrogen sulfate.
And what is,
This is that without Lewis structures and mechanism. This is the overall reaction that allowed us to form our electrophile. So part 1 is forming the electrophile. Amarachi is praying that they're just like write down the chemical reaction because that's plenty of writing. Audrey's like, I have no problem if they say, draw me that structure. I just throw down a Lewis structure. If it's really a Lewis structure, Audrey being better than me would put in all of the lone pairs. And then Brecken just freaking weeps if they say, show the mechanism for this, because this sucks. This is bad. It's a lot. But it's in your notes, and the hope is that Mohab never really has to review that. Is that fair? So the expectation is that everyone can write the equation on the right in black. The expectation is that most of you can draw a compelling looking Lewis structure for NO2+. And the expectation is that if we dug through your notes, you would find this miraculous electron pushing, and you would hope that you never had to show anyone you knew how to do it. Again, I think I can find one test question where they asked for this, but on the whole, that is not a focus. The focus is the equation on the right, so that gets the star, and that's the one that you're going to come back knowing how to do. It is called nitronium. Nitronium. Now that we have made our nitronium cation, we are going to engage in part 2.
And what is this part 2 called?
It could be called making nitrobenzene. The two ingredients that I have at hand are benzene. I am showing this special hydrogen. What's special about it is that's the one that's going to be substituted. I could draw all 6 hydrogens, but it gets confusing to me. I just draw the one because I want to know where it's going. It helps me to understand the process. So it's your call how you want to convey this, but I'm showing you my suggested way. So I have benzene and I have nitronium. If you wanted a Lewis structure of nitronium there, that would be swell. Arrows always go from electron-rich places to electron-deficient places. The electron-rich place is this ring of electrons in benzene. So we are going to draw an arrow from the electrons in benzene to the nitrogen. Deficient.
So we're drawing.
So we're saying that 2 electrons from that ring are going to go and attack the nitrogen. They're going to form a sigma bond to the nitrogen, and we are going to end up with a cation intermediate. When y'all are in a different mood, I would give you more details, but the mood I see today, this is the level of detail you're getting. What will give me full marks on the exam? You're going to notice that my intermediate has some features. My carbocation intermediate has a plus sign. That's because if I look at the stuff that are reactants and I add up their charges, I know that I have to have the same charge on the right-hand side. So the left-hand side being positive means that the right-hand side is positive. You're going to see that no longer do I have a ring that shows electrons are delocalized around the entire system. That's because this carbon right here has 4 bonds. It's no longer part of the delocalized world. So I have both broken my ring, so it's not continuous, and dotted it. I have put the positive charge in the center of the ring to indicate that it is delocalized around all of the carbon atoms. In a different mood, when there was less math test or whatever the heck's going on in your life, instead of drawing this with the circle, you can draw resonance structures. So you can use the cyclohexatriene model and show all of the resonance structures that make that state, that carbocation intermediate, relatively stable. Benzene does not want to give up electron delocalization. What we find in this intermediate is that it had to make a concession, but it didn't give it up entirely. So if you draw more of the details, you can see that there are still a number of resonance states, just that particular carbon is excluded from having, resonance. The plus is because this has a positive. And so if the left side of your equation has a positive, the right side has a positive. And the plus is delocalized around the ring.
The plus, so the positive inside shows that it's delocalized around the ring.
The positive inside is trying to denote that the charge is delocalized around the ring. And so all of you who remember the positive inductive effect was all about sort of delocalizing positive charge. Can't really delocalize positive charge, but you know, that spirit of sharing the missing money. We're seeing the same thing here. We are not going to use the words positive inductive effect, but the spirit is the same. We are spreading out the absence of those electrons over
And
multiple
it's
sites.
positive because the part on the left is positive.
So whenever the reactants have a net charge, here it's plus, the products have to have that same net charge.
And that's also why the plus is there.
That's why I have a plus there. So I'm saying when I look at this to try to give you the mark, I need to see an open ring that's dotted, and I need to see a plus sign, and I need to see that new single bond to the NO2. That's what I'm looking for to give the intermediate is good looking mark. Yes.
Is the carbon attached to the NO2
Yes.
always excluded from the resonance?
Yes. Because it has 4 single bonds.
Okay.
It can't do any pi bonding. Okay. You might recall back in part 1 that we made HSO4 minus. In my head, it is best to come back to this HSO4 minus at this point and to take that carbocation intermediate I do not always redraw this, I will admit it. And what I'm going to do is I'm going to take the minus on the HSO4 and attack that H. And then I'm going to donate this H's 2 electrons to the ring. So the HSO4 minus is a conjugate base to sulfuric acid. It is going to come and steal a proton. What is it going to become? H2SO4. At the same time that happens, the 2 electrons that were in this sigma bond are going to go crashing back into this ring. That's going to take away this guy's positive charge because we took an H plus away from it, and it's going to make the ring connect. And so we are going to make nitrated benzene. Woo. What role does sulfuric acid play in the nitration of benzene? It is a catalyst. It is recreated at that last stage.
So H2SO4 is the catalyst.
That's right. We used it in the beginning to protonate our nitric acid to make our electrophile. But at the close of this reaction, we returned the proton to the hydrogen sulfate, recreated the sulfuric acid, and acted as a catalyst.
But don't we have to add the water?
We already made the water. It's just sitting there, doing nothing.
So we don't have to put it on.
No.
Why isn't there an arrow going from the hydrogen to the H2SO4 because you're moving it?
Because electrons move, not positive things. So I am showing that the oxygen has a lone pair of electrons. It's swimming up to this H plus and stealing it. And we are allowed to do that from the minus sign so that we don't have to draw the structure of, sulfuric acid that Brecken asked me to draw a minute ago. That's another 4-mark mechanism. The arrow, the intermediate, the arrow, the product.
We have to explain it,
You need to draw it.
draw it, but
So Sophia, the question about benzene is, hey, write the mechanism for benzene being nitrated. And this is the answer. And that's why I'm saying there's exactly one question and one answer, and it's a question as to whether Brecken's gonna memorize it or not. Like, there is no way that you would have come up with that idea.
The electrophilic substitution, like we only need to know the nitrogen.
That is the only one that is in our syllabus. So bromine works similarly, but we have to make a Br plus electrophile. That is the role of the ferric bromide. That is not in our syllabus, but the spirit is the same. We need an electrophile, and in that case, it's Br plus.
Where does the arrow go from the HOSO4 minus to H and then turns to H2SO4?
So
You're getting rid of electrons and go to the hydrogen and steal.
So that's what HSO4 minus looks like. And what we're saying is that we're gonna take this lone pair right here on this negatively charged oxygen, and it is gonna go find that hydrogen. I lost it when I was drawing, I apologize, I wasn't trying to And so it's gonna make a coordinate covalent bond to that hydrogen. So it's gonna abstract an H plus. This H is gonna leave behind the electron it used to have in that bond, push it into the ring and make that ring neutral. So there's nothing wrong with drawing the structure, I just know I don't get marks for it. Like, again, normally I do this with resonance structures, I read the room and didn't do it. So usually I do part 2 hard way, and I say, you know, you don't have to take this down in your notes, everybody, I'm just gonna show it to you. And today I was like, yeah, we're not gonna play that game. This is what you need in your notes, this is what you need to be able to write down.
For part 1, we have to do the block equation.
So for part 1, you must know the black equation. For part 2, you must know what's on the center board. Perfectly said, Aditi. Amarachi.
So if the electron from the HSO4 are going onto the hydrogen, how does the hydrogen go, like, how does it make the
So these 2 electrons are going to become a covalent bond to that hydrogen. And this hydrogen has 2 electrons here. Those are going to end up in the ring. So that's how that works. So we stole an H plus. That's what made this H2SO4 neutral. And we left behind the electrons to make that ring neutral. Did that help a tiny bit, maybe?
Is there a part 3?
No, this is the whole thing. It's that easy. Do you want part 3?
No.
There you go. It's back to looking good. Yes? So to nitrate something is to put an NO2 on it. Why are we doing it? Anyone's guess as to why they chose this reaction. If Audrey lets me crank this temperature up, instead of 50 degrees, she lets me go to the 150 I want it. Instead of getting 1 nitrate, you can get multiple nitrates, and you know, your resident pyro Aditi is going to tell you that trinitrotoluene, that would be NO2, NO2, and a methyl group here is TNT. We're also going to reduce nitrobenzene to make aniline. Aniline is used in the tanning of leather and the dyeing of leather. So, I mean, I feel like it's like vaguely industrially applicable, but I don't feel like we ever talk about it that way. Benzene is a good carcinogen. It's oxybenzone that's in that. Yeah, so it's not benzene. You can't get benzene in sunscreen. I think that, but it's, I mean, it's got that name because it's got that kind of structure. You've learned your last mechanism.